Our last section in this chapter, section 8, is about acid-base titration. An acid solution turns a permanent pink when the endpoint is reached. Our learning goal is to calculate the molarity or the volume of an acid or a base solution from titration information. Titration is a laboratory procedure used to determine the molarity of an acid. It uses a base such as sodium hydroxide in the burette to neutralize that acid. There is a known volume of an acid that's placed in a flask along with an indicator. That is super important. We have to know the amount or volume of the acid that is in that flask. The indicator that is put into that acid is usually phenolphthalein, and it's colorless, and it changes the color of the solution when the acid is neutralized. The acid solution briefly turns pink when the base is added, but that pink quickly disappears once the solution is mixed. Once you kind of swirl it around, it will go away until it reaches the end point. The indicator then has a permanent pink color. The volume of the base is then measured in the burette. We knew our starting point, and then we measure our finishing end point. The molarity of the acid is calculated using the neutralization equation for the reaction, which we'll get to in a minute. If we have hydrochloric acid in our flask, and we are neutralizing it with strontium hydroxide that is in the burette, here is our neutralization reaction. We know that H will join with OH, giving us water, and strontium will join with the chlorine to give us strontium chloride. We then go and balance the equation. Here's a sample problem. If we use 16.3 milliliters, that would be the base that's in the burette. So that's how much volume, and there's the concentration of the strontium hydroxide that's in the burette. It's used to titrate the hydrochloric acid, and here's the volume of the acid that we put in that flask of gastric juice. What is the concentration or the molarity of the acid? Well, molarity, we know, is moles per liter. So we need to get this milliliter into liters first. So let's divide by 1,000 or move our decimal point back 3 spots. So we have 0.0163 liters of a 0.185 molar. And remember, that's moles per liter. Check this out. If I have 0.185 moles of strontium hydroxide per liter of strontium hydroxide, and I multiply it by that volume that we used, the 0.0163 liters. Notice that liters and liters will cancel out, leaving me with moles of strontium hydroxide. That's our first starting point. My calculator gave me 0.00300155. That's how many moles of strontium hydroxide was needed to neutralize it. Once I know moles of something, I can do my HOP from strontium hydroxide, moles of strontium hydroxide, and look at how many moles of hydrochloric acid that ratio is. I have to have my moles of strontium hydroxide on the bottom. That would be 1 for every 2 moles of HCl. Let's do that next. So we're going to take our answer and times it by 2. That gave me 0.006031 moles of HCl. Now remember, molarity is moles per liter. Hey look, we know the volume of HCl that we used. We just need to take our moles and now divide it by the 0.0250 liters. And that should give me 0.24124 capital M of HCl. Let's look how many sig figs we want. Looks like we want 3 significant figures. So 1, 2, 3. That 2 is not going to do anything. So 0.241 molar HCl solution. Let's review what we did in this mess. We started with changing our volume into liters. We then multiplied our volume times our concentration of the strontium hydroxide, since we knew both of those values. That left me with how many moles of strontium hydroxide. Then I went from moles of strontium hydroxide to moles of HCl by looking at those ratios. Once I knew my moles of HCl, I just divided it by the volume of HCl that we had in the flask. That gave me my concentration of HCl. Here is this work all in one part. We took our milliliters and went to liters, then multiplied that by its concentration. So liters times concentration. Then they multiplied it by the mole ratio. And then they took that answer and divided it by the volume of HCl to get 0.241. Take a minute to look over the learning goal for this section. Let's do a few practice problems. Why don't you pause the video here and see if you can do A and B. H2CO3 is an acid. In fact, it's carbonic acid. Iron 3 hydroxide is a base. It's FeOH3. Pause the video here to try A and B. Let's look at A first. Let's find the acid-base conjugate pairs. HBr, and if I look at my products, Br minus is going to be its pair. Now let's figure out who has more H's. Well, that's HBr, so that's going to be my acid. So over here I've got my conjugate base, my other two, H2O and H3O. H3O has more H's, so this is my conjugate acid, and this is my base. Then I have Cn minus. Its match is going to be HCN. Obviously this has more H's, so this is going to be my conjugate acid. Therefore the Cn minus is the base. H2O and OH. H2O has more H's, so this is going to be my acid, and OH would be the conjugate base. Why don't you pause the video here to try A and B. We have HNO3 reacting with water, and it says water acts as a base. So water is going to be a proton acceptor, so that H is going to donate to H2O, so I would have H3O as a product, leaving me with NO3 minus. The second one, it says we have hypochlorite, ClO minus, reacting with water, and it says water is acting as an acid. So one of those hydrogens is going to give away to the ClO, giving me HClO. It's no longer a minus, it's now neutral. And H2O, since it lost one, leaves me with the product of OH minus. Pause the video here for A and B. HCn's pair is going to be Cn minus, and SO4, 2 minus, is going to be paired with HSO4 minus. It's not asking who's the acid and who's the conjugate base. H2O's pair is going to be OH minus, and S, sulfide, -2, is going to be with HS. Pause the video here to try this problem. Let's look to see what we have here. HF, and its buddy on the other side is going to be F minus, and we have H2O and H3O that are going to be pairs. HF is hydrofluoric acid. It's not on my strong acid list, so it's going to be a weak acid. And obviously on the right it is one hydrogen shy, so this is going to be the conjugate base. This is my acid, and it's a weak acid. So over on the right, this must be a strong conjugate base. And if HF is a weak acid, then H3O plus must be a strong acid, and it's the conjugate acid. So water would be acting as a weak base. Because remember, if I have a weak acid here, I can't have another weak acid. I have to have a strong acid on my conjugate side. And if this is a weak acid, its conjugate is going to be opposite, so it's strong, and that would be the base. If this is a strong conjugate base, then my other base, which is water, would be weak. And then to figure out if we have mostly reactants or products, since my product side are my stronger acids and stronger base, it's going to push the reaction to the left, giving us mostly reactants. Pause the video here to do A and B. Let's look at the first one. We want to find the H3O plus, the hydronium ion concentration of ammonia, and we're told that the hydroxide ion concentration is 4.0 times 10 to the -4th molar. So I wrote down our H3O plus times OH minus is equal to 1 times 10 to the -14th, and we were told the hydroxide ion concentration. So in order to get H3O by itself, we're going to divide both sides by that hydroxide ion concentration to cancel that out. So we want to plug this into our calculator. 1e, or 1 times 10 to the -14th, divided by 4 times 10 to the negative 4th. And we should get 2.5 times 10 to the negative 11th. How do we know if it's acidic or basic? Well, we just look at our concentrations given. Hydroxide concentration is 4 times 10 to the negative 4. This one is 2 times 10 to the negative 11. Holy smokes, that is a small number. Negative 4 is definitely the bigger number, so hydroxide is greater than the hydronium ion, which means it is basic. In part B, we're told that the hydronium ion concentration of tomato juice is 6.3 times 10 to the negative 5th. So up here, I use that same equation. We're told H3O plus is 6.3 times 10 to the negative 5th, so I divided both sides by that number to cancel that out, leaving me with only OH is equal to, plug this into our calculator, 1 times 10 to the negative 14th divided by 6.3 times 10 to the negative 5. And my calculator tells me that it's 1.6 times 10 to the negative 10th. Look at it. This number compared to this number, and this is greater. The H3O plus concentration is greater, so it is acidic. In the last practice problems, why don't you pause here to try A and B. And we were told for both of these the hydronium ion concentrations. So to find the pH, we just take the negative log of that concentration. Check to make sure that your calculator gives you the same answer, 11.38 for A and 9.21 for B. Please be sure to check out the rest of Chapter 14's practice problems. There's a whole bunch of them.